All right, hello, stats students. I'm here to talk about the Chapter 26 notes. Hope you're doing well. Hope you've observed through TV coverage about the coronavirus how all the number of cases looks like it's going to be a definite normal curve there, and we're all practicing our social distancing, trying to flatten that normal curve out here. So all we have left actually before we've covered all the material is Chapter 26 and Chapter 27. Chapter 26, the chi-squared test, there's three different ones. These are the tests that I loved so much, I named my second daughter Kai after them. So you know these are dear to my heart. All right, here we go. So this is the letter chi right there, and that's the squared sign. So this is why it's called a chi-squared test. All of this now is going to involve when we have more than two proportions. We've done the one prop z test in interval, two prop z test in interval, and now when we have more than two proportions, that's when we're going to know it's time to do a chi-squared test. Sometimes our data is going to be given to us in terms of percentages, and we're going to need to make them counts. Counts are just the number of people, again, that said yes to whatever question it is that we're asking. So in this example, when there's an SRS of 400 favorite car makers, and we're given the percentages, the first thing that we need to do is take 45% of 400, 40% of 400, and get each of these counts, because when we're going to enter these in the calculator and do our calculations, we need them to be counts. We're going to have three different types of tests we're going to do. There's the chi-squared test for goodness of fit, the chi-squared test for homogeneity, and the chi-squared test for independence. The chi-squared test for goodness of fit, one of the ways that you'll be able to spot it is it's going to be one row of numbers as far as your expected counts go. Your homogeneity and independence is going to be a table of numbers. So that'll be one of the key ways to tell the difference. This will be one little bank of numbers, whereas in homogeneity and independence, you're going to have a table of expected counts that you're going to use. Homogeneity versus independence, the key is going to be all in how the sampling is done. If you have independently gathered samples, that is going to be homogeneity. When the problem says that you have one single sample, and again, remember this is talking about when we have a table of numbers, that's how we're going to know that we're dealing with independence. These two will look visually the same, but it's going to be in the description about how the sampling was done that will tell you which one of these two it is. Our formula is going to be on the formula chart. It is chi-squared equals to the summation of the observed minus the expected values. The observed, again, is going to be what you actually get, and the expected will be the theoretical value that you would expect to get. So we're going to have some things to look at here as far as how to get our expected values. The chi-squared goodness of fit is going to be whatever total you have times the theoretical proportion. A lot of this, again, was the first introduction. Is going to seem fairly confusing until we actually do a problem. But if somebody says that 20% of M&Ms are supposed to be red M&Ms, and you go out and take a sample of 80 of them, then you would expect 20% of those 80 M&Ms to be red. That's what we mean by what the expected is. The observed would be the number of red that you actually get. Our degrees of freedom is going to be the number of proportions minus 1. So if I'm talking about this problem above, I have 3 proportions, so my degrees of freedom is going to be 2. 3 minus 1 is 2. When we get to a table, and fortunately our calculator is going to be able to do all of this for us in matrices, we're going to take the row total times the column total divided by the total of totals. Way back when we did marginal distributions and conditional distributions, we looked at totaling these sort of columns for our two-way tables. So we should have some practice in doing this. And again, our calculator is going to be able to do all of this for us in the matrices. Now our degrees of freedom for homogeneity and independence is going to be the number of rows minus 1 times the number of columns minus 1. And that'll be the same for both of them. Lastly, when we have this chi-squared CDF, the chi-squared value, this will be like TCDF and normal CDF, but in this case, it's always going to be the value to negative 99. There will be no negative 99 to chi-squared. Both of these, again, are going to find the probability of getting an observed value as far away from the expected value as you got. And when that chi-squared value turns out to be very big, that means that our p-value is going to be very small. We'll find things significant, and that is when we're going to be rejecting our null hypothesis. All right, we're going to move on here to the back, and first we're going to look at the new conditions that we've got to deal with. So the first one's just same old, same old. We need to have an SRS, a random sample, a representative sample, or in the case of an experiment, we just need to have random assignment to your control group and your treatment group. So for the nearly normal condition, in this case, it's actually going to be more about getting a chi-squared value that is of an, I'm sorry, misspoke. Let me start again. We just need our expected values all to be at least 5. So we'll calculate these from the calculator. We'll just analyze them. And I'll usually just have you report out what the very smallest chi-squared value was. And that chi-squared value, again, the smallest one, if it's bigger than 5, then we're going to know that all of them are bigger than 5. All right, our first chi-squared goodness of fit. Now, sadly, this is the time when I've got the peanut M&Ms all bought and purchased, and they're just sitting in my classroom where I get to hand each of you a little bag of peanut M&Ms and encourage you not to eat them first, because the first thing we do is we look and see what colors we got. So what we're going to do is actually do a chi-squared test of goodness of fit to see if the distribution of peanut M&Ms is different than the distribution of plain M&Ms. So what I have here is what the M&M company claims is the distribution of their plain M&Ms. At least they did, 8 years ago when I first created these notes. Could have changed since then. Still, we're going to compare our peanut distribution to what this claim is right here. So at this point, you would all take out your M&Ms and you would count up how many of each color you would get. And then I would ask all of you, okay, hold up how many fingers for how many of each color you got. So in this year, in these classes, the total for brown M&Ms was 23. That is how many students in statistics classes that I taught that had brown M&Ms. 64 yellow, 34 red, and so on, bringing it to a grand total of 315. So now, according to the M&M company, 12% of the M&Ms for plain are brown. If that's the same for peanut, then 12% of 315 would be the expected count of M&Ms that I would get. It's okay that we have decimals, it's just an expectation. That's sort of like the old 2.3 average kids per family, which isn't really possible. So in this case, it is okay to have decimal values here. The percentage for yellow is 15%, and so 15% of 315 gets you the 47.25 expected count that you would get here. Again, this is just understanding what the calculator does, because to tell you the truth, the calculator will do all of this for you, but you will be required to know exactly what's happening in each of these circumstances. All right, we write our hypotheses. A little tedious because we have all these different proportions, but we're just defining what things are. Piece of brown, piece of yellow, etc. They're the proportion of each color of peanut M&M. So we're going to assume a representative sample. I got these from Walmart, and so typically you would think whatever distribution factory that they came from is all the same and that there's not any bias in the distribution of colors here. As we can see, we're going to report out that my smallest expected count is 37.8. That's the smallest one. That means they are all greater than 5. So that condition is met. Our H naught is going to be that each of these, as the distribution said, that they're claimed to be 12% and the distribution of plane, we're looking to see if peanut is the same of that. The alternative hypothesis is that at least one of these is different. All right, at this point, it's time to go to the calculator here. And so it's stat, gotta turn the calculator on. Stat tests, and we're going down to the chi-squared test for goodness of fit. Chi-squared GOF. Let's see if you can see that. No, not very well. It's a letter D. Look at letter D in your calculator and you'll see the chi-squared test for goodness of fit. All right, I'm going to take a little break here and see if the other calculator shows up a little bit better. And then I'll continue this on video number 2.